Thank you again for this nice introduction, and also for organizing this webinar. I think it's very timely to have such a webinar to exchange our research experience and knowledge on the hydrogen embrittlement. And I see from the program that my topic is probably slightly different from the others. So welcome for everyone to discuss about that afterwards. And my topic will be the modeling of hydrogen embrittlement at atomic scale level. Here is our group at the NTNU Nanomechanical Lab. So far, we have 2 faculty members. In addition to researcher, postdocs, we have around 15 PhDs every year. And so far, 4 of them have defended their PhD thesis this year. And we focus on mainly 4 research areas. And we often say that we have 2 hands to work. So we use the multi-scale computational simulation method. At the same time, the multi-physical experimental techniques for the 4 research directions, including the nanostructured materials with the unique mechanical performance and its application for the petroleum engineering, and even extended to like the surface and the coating design for the smart phobicity. And today our focus will be the structural material performance under the Arctic operation, like the hydrogen embrittlement or the low temperature behaviors in this the bottom right corner here. And I will just follow this outline, the hydrogen embrittlement, brief introduction of that, and then the hydrogen embrittlement related research activities in our group, NTNU Nanomechanical Lab. And then I will give you 2 cases we have been working on in the last years. The first is about the hydrogen-informed expanding cavity model. In short, it's H-ECM. We use the hydrogen and the dislocation interaction of the single crystal nickel under the non-indentation case. And the second is about the hydrogen-induced transgranular to the intergranular fracture, and use the uniaxial stringing of the bicrystalline nickel as an example to see that. And then at the last, we'll go to the summary and the perspective. And thanks to Yuka's introduction, I don't need to mention like how important the hydrogen embrittlement in the research field. And since the 1875, first mentioned by William Johnson, and the hydrogen embrittlement has been a really old problem, but with the growing interest and from the annual publication, and we can see it's actually attract a lot of attention. And this year so far, it already have around 500 papers based on the web of the science. And it's not only old problem with the growing interest about the conventional hydrogen embrittlement we mentioned, but also about this hydrogen-powered society. And this is actually a commercial published in Nature early this year. It's based on the hydrogen energy, the carbon-free hydrogen energy experience in Japan, how this conceptual design of the hydrogen-powered society, and using the existing infrastructure like those refineries, the pipelines already exist there, and then use the knowledge from the oil industry and to just use the hydrogen to replace the fossil fuels in the modern society. And this gives the big inspiration of the new energy application, but at the same time, again, raise the new interest in the hydrogen embrittlement. And the hydrogen embrittlement research in Norway has a very long history. Thanks to the rich oil and gas resources in Norway and this very complex the pipeline transport network in Norway. So left figure shows the oil and gas reservoir along the coastline of Norway in the Norwegian continental shelf. And you will see a lot of those reservoirs there. And in the offshore operation, always we use the catalytic protection for the anti-corrosion purpose of the infrastructure. But this brings, of course, the hydrogen embrittlement problem, generate a lot of hydrogen molecules diffuse into the material and cause embrittlement. And also now, if you use those existing, the natural gas pipeline to transport the hydrogen, this hydrogen, of course, will diffuse into the pipeline. So although it's the renewed thinking of the production and the transport, but the problem is the same about the hydrogen embrittlement. And there are many mechanisms that describe the hydrogen embrittlement, but two of them, among the others, are well accepted. First is this hydrogen enhanced dislocation, in short, HED. Second is the hydrogen enhanced localized plasticity, in short, HELP. So HED means that the hydrogen weakens the atomic bond. So it works in very short range lattice dynamics scale. While the HELP means that this hydrogen, when entering into material, will shields the elastic stress field of the dislocation. So it works in a long range stress field. But it's very difficult to really identify which mechanism your material will meet, because often the two will work together at different time scales. And if we see how the hydrogen will impact the material behavior, originally, if it's a ductile material, when the hydrogen entered, we may have this the Cossey cleavage process. With the increase of the hydrogen concentration, we even have the intergranular fracture of the system. And based on the experimental observations, we can conclude that most ferritic steels are susceptible to the hydrogen embrittlement, while most of FCC metals are relatively resistant to that, except the nickel-based high-stress alloys or the super alloys. So categorizing the hydrogen embrittlement on the different metallic materials have many ways. We could use maybe like the stress of the material or the crystalline structure, its composition. However, all these classifications doesn't show any general trend in the sensitivity of the material to the hydrogen embrittlement. So that means so far we don't have any like the universal law or the principle to describe the hydrogen embrittlement. We can say it's the really like the complex material phenomenon. And the research about hydrogen embrittlement in our group has started around maybe 8 years ago. In the whole history that we collaborated very closely with the Norwegian industry. Here are the 4 research projects we have in previously and now ongoing projects. And from the title that you can see, we change from the individual materials and then come to a multi-scale hydrogen embrittlement assessment framework, and even for the safe transport of the hydrogen. And the purpose is that we could develop a kind of multi-scale assessment framework for the prediction and prevention of the hydrogen embrittlement sensitivity of the materials. And here that, since I will talk about mainly the modeling part. So this is a brief illustration of the multi-scale methods we are using for the hydrogen embrittlement. Basically that we apply all the simulation techniques for the hydrogen embrittlement, start from the nanoscale, the atomic and molecular scale, up to the dislocation scale, the mesoscale, and the continuum scale. And the questions we try to answer by all these simulation techniques will be like, how can hydrogen enter into the material? How fast those hydrogen will enter into the material? How much hydrogen can a specific material take? When the hydrogen entered, what hydrogen does to the material performance? Are we able to predict the effect of hydrogen throughout the lifetime of the material? Especially that if we understand all these questions, and the last question, how or can we able to mitigate all these effects induced by the hydrogen? If we can answer those questions, of course, it will not only help us to design the hydrogen-resistant materials, and also help to extend the lifetime of those existing materials and infrastructures. So next, I will use the two, like the examples in the atomic simulation level, how we understand the hydrogen embrittlement. The first is proposed the H-ECM using the single crystalline nickel as the model material. Second is that the hydrogen-induced, the transgranular to intergranular fracture use the bicrystalline nickel as the example model material. And let's see how it is. In this, the H-ECM model, we try to establish a predictive model to capture the on-the-fly response of the help mechanism in the non-indentation. And the reason we choose the expanding cavity model, which is originally developed to describe internally pressurized the spherical shell with elastic and perfectly plastic material. And due to the similarity with the indentation, it's very often used to describe the indentation process. So here, the main, like the issue for us is how to involve hydrogen into the original ECM model. And in this flow chart, I show you how to involve the hydrogen actually. In the original ECM model, we have the stress field, but then we can decompose it to two components: hydrostatic stress, which will drive the hydrogen, and then induce the solute drag to the dislocation. Well, the second component is the shear stress part, which will drive the dislocation mobility. And then we combine these two components at the end to derive the dynamic evolution of the force and the displacement curve during the indentation, and also the dislocation density evolution during this indentation process. And the final model shows, like here, we don't need to remember these details, just that you see that the two parameters we are interested with. And let's see how it works. Here is the comparison of the model with those dash lines with MD simulation, those bumpy curves. We can see that the model still have some deviation from the indentation. It works very well at the elastic part, but when the yield starts, it deviates a little bit. I will talk why we have those deviation. But both the model and the MD simulation predict the softening effect of hydrogen. Interestingly, that from the MD simulation, we see that the down indentation curve is not so sensitive to the hydrogen content. Here, probably because of this very fast process, so we don't really have the hydrogen diffusion possibility. That means that we have this computation between the dislocation velocity and the hydrogen diffusivity inside of the materials. So that's why maybe in the MD, that the curve is not so sensitive to the hydrogen content. But anyway, when we analyze the dislocation density Here we use the defective atoms as an index of the dislocation density. And we see that initially, the material is not so sensitive to the hydrogen, but then at the certain point, actually hydrogen dramatically decreases the dislocation density. Those straight line, green, pink, or black, just for the eye guidance, while those dots represents the dislocation density of the curve. So pink is the hydrogen-free case, while the black is the hydrogen case. We also see when we analyze the detailed those dislocation, we see that the vacancy hydrogen complex serves as the candidate sites for the heterogeneous nucleation of the dislocations. And this also verifies the model in these three parts: the homogeneous, heterogeneous nucleation, and also the annihilation of the dislocations. If we see the indentation process by the molecular simulation, left is the hydrogen-free, right is with the hydrogen case. You can easily see that in the pure nickel, that all these dislocation loops pile up at the upper part, which introduce very strong dislocation entanglement and very high dislocation density. So it has a kind of a strengthening effect to the material. Well, in the hydrogen case, that dislocation loop emitted, but instantly transport to the whole model cell. So the hydrogen actually can release the dislocation entanglement. And this is also the reason of this hydrogen-induced softening effect of the system. And let's see the experimental evidence to confirm that. So experimentally, we did the same nanoindentation on the high entropy alloys. And the left shows a representative force displacement curve. And of course, that the popping in this load displacement curve represents the plasticity onset and the development. So we take this the popping load, this initial point of the plasticity, and the popping wise here. And to compare that, in air means without any hydrogen charging. Well, from H1 to H3 means the increasing the electrochemical hydrogen charging potential. So that means the increase of the hydrogen content. Anode means then we degas the hydrogen from the material. So we again reach a hydrogen-free case. Interestingly, we see that both the popping load and width will decrease with the increasing hydrogen content. Well, after degassing, it's almost back to the hydrogen-free case. And if we replot here, this one, to this the popping load and width relation, it's very interesting that we see the hydrogen significantly lower the critical force for the dislocation emission. Left is the air and the anode case, then it's increasing the hydrogen concentration. So we see a lower force for dislocation emission. And also in all hydrogen cases, that's the increasing the hydrogen concentration will introduce the larger resistance to dislocation motion or the mobility. So it matches very well with the MD simulation. And next, let's see how this hydrogen microstructure and plasticity interactions. And here we try to explore its interaction mechanisms and to develop the mechanics-based hydrogen embrittlement criteria. And we use the bicrystal nickel as the model material. And here we have the sigma 5 grain boundary. And we use the Monte Carlo method to insert the hydrogen atoms and then to monitor the hydrogen concentration evolution. And we can see after around 5 million Monte Carlo steps, is almost the reach constant of all the hydrogen concentration, and that means it's a saturation situation already reached. And interestingly, we see that this sigma 5 green boundary trapped a lot of hydrogen atoms. And this also agrees with our common understanding that the green boundary is the trapping set for the hydrogen atoms. And then let's see how the result look like. The red curve shows the stress strain curve with different hydrogen concentration. And interesting, with increasing the hydrogen concentration, we lower the yield point and also the fracture stress and strain. If we see the dynamic process here, the left case without hydrogen, the middle one with the hydrogen, and inside here, left is microstructure evolution and right is the vacancy distribution. And both in the same time scale. And interestingly, we see that in the hydrogen case, the twinning or the dislocation occurs much earlier. And the vacancy concentration is much higher compared to the hydrogen-free case. And even at the end, that the hydrogen induces this void occur at the green boundary compared to this hydrogen-free case at the inertia of the interior of the grain. So it induces a fracture transition from transgranular to the intergranular. And if we go a little bit more detail here, we can see this two cases with sigma 5 and sigma 9 green boundary, both found out this softening effect of the hydrogen to the original stress and strain curve. And if we analyze those the modeling snapshots, we can see that in the hydrogen case, the onset of plasticity occurs earlier, and also the void occurs much earlier if we see those strain level listed on the top. And both cases, we found this fracture transition to the intergranular. And we compared many different cases and get out this vacancy and the fracture mode distribution actually. And left means the transgranular, and right means this the intergranular. And we see this the intergranular fracture fraction change with the vacancy concentration. And there is a critical vacancy concentration here for different types of the green boundary. So this gives us the possibility to quantitatively predict the intergranular fracture induced by the hydrogen presence.
Okay, maximum 2 minutes or 1 minute.
Jianying. Yeah. Here is experimental evidence. It follows our prediction that when hydrogen occurs, the fracture mode changes from the transgranular to this mixed mode and to the intergranular. So it matches perfectly with the simulation results. And come to the summary. Here we can see that both the help and head mechanisms are demonstrated by the molecular dynamic simulation in the model material, nickel. And we developed this hydrogen-informed ECM model, which of course not work perfectly, but need extra terms to describe the dislocation evolution. We, for the first time, predicted this hydrogen-induced transgranular to intergranular fracture transition. And this gives the quantitative relation of the fracture mode with the vacancy concentration. And we are doing the further research here. And the perspective from this is that if we could predict the hydrogen vacancy, dislocation, and fracture from the atomic level and up to the continuum level, and finally predict the material behavior using a void-based predictive model at all the scales. So far that our answer is yes, it will be possible. This will change the current treatment of the hydrogen embrittlement from the binary manner to later predict the when this material is susceptible to the hydrogen embrittlement. So gives the dynamic prediction of the hydrogen embrittlement. Yeah. The last is that, okay, it's the complex, challenging, exciting, important problems. Thanks to my colleagues, all listed here, working on the hydrogen embrittlement problems in our group. Thank you all for your attention.